So I think we've covered enough about the optics and the photolithography stages and photomasks. Let's now go on to the other technologies, the main CMOS technologies that go into creating the various different layers. So we know how to pattern them and the things that go into patterning the layers, but let's go into more detail on the actual various different layers in order to create the integrated circuits in silicon. So the main CMOS technologies, up until now, we've been talking about an N-well process. So we start with a P substrate, and all NMOS devices are in the P substrate and share the same bulk body, which is that P substrate. And the gates of your NMOS devices are over the P substrate. So they have certain characteristics based on that P substrate that are all the same. As opposed to in the N-well itself, we have a certain doping for the N-well, and our PMOS devices are in that N-well, and the characteristics of the PMOS devices are going to be determined in part by the doping in the N-well. As opposed to an N-well process, we could also instead do a P-wells process, and this kind of flips the P and N devices. If we have a P-well process, we would do a P-well in an N substrate. So we'd start with a silicon wafer that is doped N-type doping. So in this case, all PMOS devices would share the N substrate as their bulk/body, and their gates would be over that N substrate. In both of these cases, the devices that are not in the well are determined, their gate structure is determined by the substrate doping. So for the P-well process, all NMOS devices would be inside of a P-well, and their characteristics of the NMOS devices in the P-well are determined by the doping of the P-well. And you can have separate P-wells such that some NMOS devices could have one bulk body and other NMOS devices in a different P-well could have a different body. As opposed to an N-well or P-well process, we could do a twin-well process. For a twin well, we still have one of the wells is going to be, so if we had a twin well process using a P substrate, the P well in the P substrate is still basically shorted to that P substrate. So if we have a twin well process using a P substrate, all NMOS devices still kind of share the same voltage as the bulk body, but we could have the P wells in the P substrate have a slightly different doping than the P substrate. So by doing a twin well process, it allows you to optimize some of the characteristics of the transistors for each transistor type, but one of those transistor types, like for example, if you had a twin well in a P substrate, the P well in that P substrate is still going to be shorted to that P substrate. And so the NMOS transistors would still share the same bulk body voltage, even though they might have a slightly different doping concentration of their well. Now comparing versus each of these processes, there's something called the triple well process. The triple well process allows you to actually individually have your NMOS and PMOS transistors in different wells. So both NMOS and PMOS can be their own well and have a different voltage for their bulk body. So you do not have to share the same bulk body with all transistors of the same type for either NMOS or PMOS. This allows us to isolate logic and have different power supplies and also different ground supplies for different logic. And by doing that, it allows us to have some circuits like sensitive circuits, analog circuits, could be connected to less noisy power supplies and ground supplies. I'll go a little bit more into the triple well process in the coming foil. So in this figure, we can actually see the triple well process is actually shown how you would go about creating it. Here we're starting with a P substrate, like our typical process has been, and we have an N well off to the right, which is our standard N well, and we can put PMOS devices inside of that N well. And so we have P plus diffusion regions, and then an N plus diffusion region, which is the contact of a voltage contact to the N well. On the left-hand side, you can see what we have is our NMOS devices. Instead of the N plus diffusion just being in the P substrate, what we do is we first will basically diffuse a really deep N well as our first step. And this typically might even be done before the normal N well. So we diffuse a really deep N well, and this deep N well basically acts as a barrier region, if you want to call it that, between the P substrate and the P well. If we were doing, like, let's say a dual well process, we would just do an N well and a P well. But if we did dual well, the P well would be shorted to the P substrate. By doing this deep N well before we do the P well, we get basically a barrier region between the P substrate and the P well. So first we'll diffuse a really deep N well, then we diffuse a P well, and then we diffuse the N plus and P plus regions to make the connection to the P well and the N plus connections for the NMOS device. And this allows us to have all of our P well regions can be totally separate from each other and also separate from the substrate. So basically the reason why you might want to do a triple well process, you can see that it's an additional step to create the deep N well, and it's also an additional step to create the P well. So it's more costly, and it could potentially have effects on your yield versus just using NMOS devices in the P substrate because of the additional steps. So some of the reasons why you might want to use a triple well process is sensitive circuits like analog circuits, and some high density, low power memories can be really sensitive to power supply noise, and so you might want to have separate power and ground to your P and NMOS devices for these sensitive circuits. Another thing, maybe you want a separate power and ground supply for really high speed digital logic in order to have high speed digital logic creates lots of noise, and maybe you want that to be on a separate power supply that is not being shared with more sensitive logic. And then the final note about deep N wells is doing the deep N well, you can see it's a lot deeper than the regular N well and the regular P well. In order to implant ions that deep, usually we don't do that through just diffusion. We'll shoot ions at the substrate and try to get them implanted deep within the substrate, and then do an annealing step, a high temperature step afterwards, to have them diffuse out and diffuse into the silicon crystal afterwards. But that requires a really high mega electron volt implantation step. And one of the things this does is creates what's called a retrograde well. So you're implanting the ions, you want them to be implanted at a deeper depth. And so the concentration of the ions is actually going to be higher, deeper into the substrate than when you just do diffusion from the surface. Your highest concentration is at the surface of the silicon. So this retrograde well actually has some effects on how the devices behave. And then the third issue with deep N wells is, in order to stop this really high ion implantation in areas where you don't want the deep N well, you have to make sure that those ions don't make it through your photoresist in areas where you're trying to block it off. So it requires a really thick photoresist in areas where you don't want the well. And this can cause a little bit of some issues that we'll get into in the next foil. So this is showing, as I said in the previous foil, when we're doing a deep well implant, what we need in order to stop the implant from going through the substrate in areas where we don't want the well, we need that resist layer to be really thick. And so it might be, 2, 3, 5 times as thick as what your normal resist layers might be for other steps. And because that resist layer is thicker, when you get ions that hit the very edge of the resist, as is shown in the figure above, those ions, some of them will scatter off to the right toward the well, some will scatter, maybe into the resist and get stopped there. But the ones that get scattered to the right and will cause additional extra ions, so more ions than you want typically, scattering into the well at the very edge of the well as it's defined. And so since you'll have extra ions scattering into that area, it means that the concentration of dopants at the edge of the well is actually going to be higher than the concentration of dopants in the middle of the well. And this will cause transistors that are actually being, if you have transistors that are patterned at the edge of the well, they could have a different threshold voltage, a different mobility to their carriers through the gate. And you don't really want to have different properties of your transistors typically. And so this is what's called the well edge proximity effect, meaning that transistors that are near the well edge will have different properties to them than transistors that are in the center of the well edge. So if you're using this deep kind of well, you might have additional design rules saying that you need transistors to be farther from that well edge. And so it's just something that you need to be aware of and pay attention to and design accordingly. The other thing is transistors in a P well that's in a deep N well will have different properties than transistors that are just in the P substrate. So if you do design some transistors in your P substrate and some transistors inside the P well that's inside the N well, they're going to have, the P well has a different doping concentration than the P substrate, and so you will get different properties of those transistors. And so you have to make sure that you model basically transistors that are in the P well differently, either with different threshold voltage or whatever the properties are that are different on that transistor. You have to make sure that those get modeled differently than transistors that are inside a P well that's inside the deep N well. Next, let's talk about one of the most important layers in all of your integrated circuit design is your insulator or dielectric layer. You might ask, why is that the most important? You'd think that the transistor layers or metal layers would be most important, but one of the reasons is because your insulator or dielectric is used pretty much everywhere in your design. Between all your wires, between your various different layers, you need to make sure that you have a good insulating, you don't have shorts, The better insulator you have, the less capacitance you have, which serves, the more capacitance you have, the more it slows you down, the more power you have to use in order to switch things. And so reducing your capacitance is a huge deal. And then, of course, your insulator, dielectric, is used as your gate region. You need a dielectric for your metal oxide semiconductor, the oxide part. You need to have a really good dielectric there in order to make sure your gate functions well. So silicon processing does require a good insulator between your various layers, your gate oxide, your gate, source, and drain contacts. The better insulation you have between them, the faster your transistors are going to be, between all your metal wires and between neighboring transistors. And one of the reasons silicon has dominated in the IC design area, there are other semiconductors out there, but one of the reasons silicon is dominated is because silicon dioxide, which is the main dielectric used with silicon, is pretty easy to grow or etch. The silicon dioxide is easy to process, and so you can use it for getting thin gate oxides. You can use it for thick field oxides in areas underneath regions where we don't want any transistors formed. We don't want to form an inverted channel underneath areas between transistors when we have metal wires or polysilicon running over those areas. And so having a good dielectric is very important. Now, in silicon, there's multiple different ways that we can form these oxides. One of the quickest ways is using what's called wet oxidation. So we put, if we put silicon into a furnace along with water vapor and heat it up, you can form a fairly, that water vapor will basically start reacting with the silicon surface and forming silicon dioxide. It creates a thick oxide, creates it fairly fast, but it's a little bit lower quality oxide. But wet oxidation is normally used in areas where we need a pretty thick oxide, so in our field regions where we don't want our transistors. Another way to form oxide is what's called dry oxidation. Instead of using water vapor, we use pure oxygen flowing over the wafer while we heat it up. And this will grow oxide pretty slowly, but it forms a really high quality, predictable thickness, and we can form our gate oxides using a dry oxidation. For both wet or dry oxidation, since we're using oxygen to react with the silicon of the chip, it will consume some of the existing silicon in order to form silicon dioxide. So both wet and dry oxidation will consume the existing silicon surface layer in order to create the silicon dioxide. A different way of forming oxidation that doesn't consume your silicon layer is what's called atomic layer deposition, or ALD. This is where we'll expose the surface of the silicon or wafer to different chemicals, and one chemical will form on the surface and then expose it to a different chemical, and by alternating which chemicals, it will slowly build up oxide, single layer by single layer, and this does not consume any of the existing silicon surface layer. So this is a third way to form oxides. It's more time intensive and more costly, but it's a way of forming oxide without consuming the existing silicon.
So as I said in the previous slide, the insulating or dielectric layers in silicon are a couple of the really important processing steps. So let's go into a couple areas of generating insulating layers that are actually very important to modern IC design. So the first one of those is what is called shallow trench isolation. So as I said, we want to not just have PN junctions, reverse bias PN junctions, as our isolating layers because they have a lot higher leakage currents through reverse bias junctions. So instead of isolating our N-well and P-well areas by PN junctions, we'd rather do it by oxides. So shallow trench isolation is one way to do it. Like I said, so if you see in the area or in the diagram above, we have some different well areas, an N-well area and a P-well area. And we used to, in older process technologies, just grow a really thick oxide that goes all the way down the depth of the well, but then that caused lateral diffusion as well of that oxide. So there was a fairly large distance between P-wells and N-wells. So in shallow trench isolation, what we wind up doing is trying to basically build oxide between the P-wells and N-wells by forming a trench of oxide, and basically the trench, the width of the trench is mostly kind of independent of the depth, and so we can get much better density, and we get a lower junction leakage of our source and drain areas and well areas because we have oxide rather than having PN junctions there. So we'll go through the steps in the following foil. So now we'll go through the actual steps in order to produce the shallow trench isolation between P-wells and N-wells. The diagram shown above shows the various different steps. The first two parts of shallow trench isolation are forming a pad oxide. So if we start with a silicon wafer that has the P-well and N-wells already formed, and then of course there will be some P substrate between the wells that will be on the wafer, and we'll have basically a flat wafer. But before the first step shown in the figure above, before the trench etch, first we need to form a pad oxide layer on top of the entire wafer and a nitride, silicon nitride layer over top of the pad oxide. And so then we'll have a flat wafer with pad oxide over the entire wafer and silicon nitride over the entire wafer. Then we'll use basically patterning steps. So we'll use photomasks and photoresist to form patterns that expose only the areas where we want the trench etch. And so once we have gaps in the photoresist that expose the areas where we want the trenches, then we selectively remove the silicon nitride from just those areas where we want the trench. And then we can also be etching the silicon, so we'll wind up doing a trench vertical etch in the areas where we want the trenches, and we'll etch that down till we get below the area of, or around the area where the P-well and N-wells are ending, you know, how deep they go into the silicon. So once we've done that, we can remove the pattern photoresist, and we'll have the trenches. The next step is we want to perform a oxide. We grow a thin layer of liner oxide in only the areas where we have exposed silicon. So we can do we can grow that through like a dry gate oxide type growth, and it won't grow, the oxide won't grow on silicon nitride because it only the oxidation will only react with pure silicon, but not with silicon nitride. So we get that thin layer of oxide. Liner oxidation is what it's called for that step B shown in the upper right of the figure. Now that oxide forms basically a seed layer for growing a thicker oxide to fill the trenches, and this is done using chemical vapor deposition. And the chemicals that we'll use in this CVD step will only grow, they'll react and selectively grow on existing oxide, but they won't grow on the silicon nitride. And so we will grow an oxide layer inside the trenches, but not on the rest of the wafer where it's protected by the silicon nitride. So then that kind of fills in the filling the trench with a silicon oxide dielectric, which is the step C shown in the figure. And then we go on to the final step where effectively we remove the nitride and the pad oxide layers using a chemical mechanical polish, also called CMP. This is a really important step in not just for shallow trench isolation, but for many other layers that we'll be doing in the processing steps later. CMP is effectively, it's a mechanical grinding of the wafer. You kind of rotate the wafer and have some additional movement of the wafer in order to grind the wafer with also a chemical slurry, if you will. And so you have both a mechanical grinding and chemical reaction going on to basically remove layers from the top of the wafer and try to remove layers as well as planarizing, because you want it as flat as possible for the following steps. So now that we've completed our shallow trench isolation, we now have a wafer that has oxide region between our P wells and N wells, providing good isolation for capacitance as well as leakage. And now we can form our gate oxide over our wafer. So the gate oxide step can be performed. We can either form a single gate oxide over the entire wafer, or we can perform it selectively in certain areas, and I'll get into that next. But the gate oxide that we form, we can either try to form a really high quality pure silicon dioxide layer, which is used for a lot of, historically that was maybe used more common years ago. More recently, you might also have that pure silicon dioxide layer overlaid with an oxynitrided oxide. This is blending the silicon dioxide with some nitride in order to increase the effective dielectric constant of your gate oxide. So basically an oxynitrided oxide effectively it decreases the effective oxide thickness. So you have a measured thickness, but the measured thickness acts like it's a thinner oxide, and in fact you can get a higher electric field than you would normally predict based on the thickness. And so since you have a physical layer that's a little bit thicker, but it acts like it's a thinner oxide, this allows you to get a little bit less leakage through the oxide. Keep in mind, gate oxide, silicon gate, you expect the gate to have no current through the gate, but as you get to thinner and thinner oxide, you actually start getting some tunneling current and stuff through the gates. So this allows you to get less of that tunneling current through your capacitive gate, because you expect capacitors to have no DC currents. And so this allows you to reduce that parasitic tunneling current that you would otherwise get, and get a better electric field for a given thickness. So I mentioned before, another thing that you could do though is rather than forming an oxide over the entire wafer, you could do it selectively. And so if you wanted to do a selective oxide, so you might do one oxide thickness in an area of your wafer where you have digital logic, and then a different oxide thickness in an area of your wafer where you have analog logic. A lot of times analog devices, transistors, you want different characteristics from, and so that's a good way to get different characteristics from analog transistors would be to have a different oxide thickness of the transistors. Also, you might have, rather than analog transistors, you might have certain areas of your logic where you know it's non-critical from a speed standpoint, and so you just want it to be very low power. And so you could make low power areas have a different oxide thickness, a thicker oxide that would have less leakage currents and lower power. So keep in mind, these seem like they're valuable things to have, which they are, but every time you add additional processing steps, so having 3 different or 2 or 3 different oxide thicknesses across your wafer increases the number of processing steps. It's going to increase your costs. Time through the fab is going to be longer, and it might even decrease your yield because you're going through more processing steps. So everything you add that has a positive effect might also have some negative effects that you have to weigh the positives and negatives against each other.